Thank you so much, colleagues. Welcome to the second session of sector sustainability. I don't know whether you wanted to take 5 minutes of questions from the previous colleague, or are we happy to proceed with the next speaker? Proceed. Okay. I think most of the information will take them online, and we'll take it from there. So our next speaker, it's going to be from Atlantis Foundries, which is one of the companies we support a lot from the NFTN side. But in this case, they'll be presenting on the work they've done with the NCPC regarding the energy case study from their side. And Andre will introduce who Atlantis is. They are one of the 5 automotive design companies in the country from the automotive sector. There's a lot of history where they came from Daimler Chrysler, VW, and all that. So we can give you the history, at least from that part. I would say welcome home. So because that's where I come from in terms of my background. I come from the automotive sector, especially from the Dysamatic line. So over to you, Andre.
Hi, good afternoon, everyone. Is this too loud? So I want to take you guys through our journey on what we did to save energy and what we actually achieved. So moving on, but doesn't want to move on. Let's use the cursors. Start advancing. Okay, short bio. I'm a plant engineer working at the foundry. I've been working there for the last 12 years. My main duties are for automation and control. It's also substation maintenance, and I consult on projects. Some of my newer activities is energy efficiency and power quality. But more about our company. Yes, we do manufacture engine castings. We're part of the Daimler truck group, so our castings are for buses and trucks. We were established in 1982, and we were then known as ADE. A lot of stuff's happened. Now we're known as Atlantis Foundries, and we're in the Western Cape with about just over 800 employees. And when it comes to electricity, that's what I'm going to talk about. We have a notified maximum demand of 31 MVA, and it's supplied to us at 11 kV. But now I want to take you through some of the actual stuff we did. And first up was, and this is the normal first step for everyone looking at saving energy. It's changing all your incandescent and fluorescence to LEDs because they do last longer and they are better. There are disadvantages, meaning the higher initial cost. But something that's not mentioned as much is that they are also more prone to propagate voltage flicker, which leads to the whole sick building syndrome. That's part of it. And the sick building syndrome, especially a voltage flicker, when the voltage that you supply to a luminaire flickers, that gets translated into luminous flicker. And that can cause headaches and nausea and stuff like that. So we changed all of our incandescent high bays and stuff to LEDs. But what we also did was we installed a maximum demand controller. Now we are on the time of use tariff, and as you guys know, it's broken down into standard, peak, and off-peak time slots. So you pay cheaper for electricity depending on when you use it. The other thing about the energy tariffs is that besides the fixed cost that you pay to your energy provider, You also pay for the amount of energy you use and also for the rate at which you consume it. And that's what we call the demand. Now, the thing about demand is that it only gets monitored for peak and standard times, not off peak, which actually poses a saving opportunity. So, what we did was we installed a maximum demand controller. So, when it's standard and peak, we limit ourselves to 25 MVA, but when it's off peak times, we allow ourselves to go up to our notified maximum demand of 31 MVA. Now, I have to mention that this is not really saving energy because you're actually just shifting your load. But at the end of the day, it does reduce your demand charges. So you do feel a decrease in the bill you pay. And that's basically sort of what we're also after. Moving on. You would also know that power factor correction reduces the power seen by the utility. Power you pay for, which they call the demand. Now, there's traditional ways of doing power factor correction, and when I say this, that traditional, I mean where you have a capacitor bank that's being switched by a contactor or a solid state device, and you could even go the next step up, where if you have a plant where we have power quality issues, for instance harmonics, you'd put a reactor in front. Like I mentioned, you've got the traditional type of power factor correction equipment. But now the problem with the traditional ones are that they've got, firstly, two issues. They've got fixed step sizes, and the other thing is there's usually a delay. For instance, if you had one particular cap bank energized and you de-energize it, you'll have to wait what's usually about 60 seconds before energizing it again. So what that leads to is, if you look at the orange line, that's what your plant demands. And the green is the response of your power factor correction equipment. Two things are immediately clear. The stepped response, because it's fixed capacitor step sizes, and the other thing is the response is delayed. What that leads to is that you see all the hashed out areas, which shows that you've been undercompensated. And this is usually the case with a traditional setup. You're either in a state of over or undercompensation. And specifically this undercompensation area, that's a potential saving. Now that's the traditional one. What we did, because we've got power quality issues as well, we went for SVGs, which are static VAR generators. Now, they've got a lot of benefits and they're actually very nice. Firstly, they've got a continuously variable response, meaning that there's no more delay. So what your plant requires, it gets. And they're also low maintenance, and because the response time is so quick, they have a quicker payback period. Okay, you guys can hear me fine? Sorry, man. They also take up less space than your traditional power factor units. And what was important for us is that they are immune to and they don't amplify harmonics. But they do have certain disadvantages. And among those are that they, just like with the LED technology, they have a high initial cost. And they do generate heat. For instance, we've got units that are rated at 3 kVAR. And when they're running full tilt, they generate about 9 kilowatt of heat. So if you have them in a room that's not ventilated well, you're probably going to need to put in an aircon. But overall, they're great devices for doing power factor correction. Another thing we did was we got lots of cooling towers. And usually those cooling towers are a bit over-designed. Now, we had an issue where the fans were on all the time, which is actually normal. So you've got the cooling tower operating all the time, but your process doesn't operate all the time. So that could lead that the delta T of your cooling, your process water coming in and going out, that would sometimes drop to low. And that's not really good for process. You want things to be more stable. So what we did was, we started to monitor what the actual delta T was. And we programmed ourselves bands so that if you need this much cooling capacity, you have all the fans on. If you require less, switch the fans off. And we had these fans controlled through soft starters, so you don't have all that inrush and stuff. And it worked out well. We saved a lot of energy actually. Another thing is, like we've got lots of cooling towers, we've also got lots of dust extractors. And here the same thing applies. They are usually over-designed because initially, whoever is your solution provider doesn't know what your plant requirements are, so they would rather stay on the safe side and they over-engineer it. Now, in our case, because the fans were over-designed, suction was very strong, so there were dampers downstream, and they used to throttle the dampers to create a pressure drop, thereby regulating the suction. Now, if you look at the affinity laws for the pumps, you can see that first off, it makes sense that your amount of flow, your volumetric flow, is proportional to your speed. That makes sense. But what the affinity laws also tell us is that there's actually a key relationship between your speed and the power consumed by your system. So what we did was we partnered with a company who installed variable speed drives on their cost. And how it worked was they calculated or they measured beforehand what we consume. And they said, okay, with our system in place, you're consuming this much less. So they get a portion of what we save, which worked out fine for us because it's zero capex from our side. But what they did was they installed the variable speed drives with all the dampers open and found out what the optimal speed was to still have adequate suction. And thereby, we saved a lot of energy. The motor in the picture, it looks small. This is actually a 132 kilowatt motor. It's the smallest one on which we did it. The biggest size was 200 kilowatt. And we did it on four motors. Moving a bit on, another thing we did was we've got a lot of compressed air. We've got a few compressors running. Now, we were in the situation where if you'd walk into the plant and it's quiet, you'd think there's snakes or something, but because you just hear. So what we did was we installed instrumentation on our normal compressed air and on our desiccant air to monitor what we consume. And then we went into the plant and we went and fixed all the leaks. Having fixed all the leaks, we then monitored what our consumption was, just to have a benchmark. And from then on, whenever there were spikes or if the trend was showing an upward curve that we couldn't explain, we'd know it's time to go and investigate. That also saved a lot of energy. The other thing is, earlier I mentioned that one of my duties was looking at power quality. What I failed to mention was that we are the source of our own misery because we've got a lot of non-linear loads and we are polluting our own electricity supply. Now, besides all the, I didn't want to say crap, all the stuff that harmonics cause, some of the stuff that we felt a lot was that we had let me give you some background. We had electronic component failures. We had drives that would fail. We had motors where the bearings would cease prematurely. And on inspection, we could see that there were traces of harmonic currents passing through the bearings. And so, overall, some of the effects of harmonics are that you reduce the lifetime of nearby equipment. And as an example, usually what you find is that your motors, so the motor takes a certain amount of energy to displace a load. Now, if that motor operates in a harmonic-rich environment, it actually draws more current because a lot of that energy goes to waste. That's energy lost. What you also find, and this we saw, was that your transformers and your cabling, they run hot. And that energy has to come from somewhere, and it comes from your utility supplier using energy you pay for. So it's like being penalized twice. You pay for the energy and you shorten your lifetime of your equipment. So what we did was we installed an active harmonic filter, and it helped a lot. we were non-compliant in terms of NRS 048. We are now compliant, but we've still got issues, and we are gonna install another harmonic filter just to clean up our supply even more. Okay, so what did we achieve? All in all, we achieved a saving in energy of 28.4 gigawatt hours, which is actually a substantial amount. And if you translate that to money that we would have paid, it comes out to almost 27 mil. But because we participated, because we did a 12L SARS application, we got a rebate of almost 7.4 mil. So that's money that we actually spent on projects being paid back. But now, this amount of energy is a lot, and it wasn't saved in 1 year. This project actually ran from 2012 to 2019. Okay, and about our journey. We approached the AIDC, and the AIDC hooked us up with the NCPC. The NCPC, on its part, did a free survey and assessment of a plant, and out of that, we got a report. And the report said, do this and this and this and that. And for a while, it sat dormant till we picked it up again. But when we picked it up and we started implementing projects, afterwards, we approached the M&V to register the project with Saneri, to do the verification, and to do the 12L application. And at the end of it, the project was approved, we got our rebate, everything was nice. Now that's how our journey was, but we are not done yet. So we do have some next steps. Now, you'll know that your maximum demand is based on the maximum load seen on any one phase in a 30-minute window. But now, if you look at, these are big plants. We're usually talking about big plants. And you've got lots of dBs sitting everywhere. Now, if those dBs are not balanced in terms of the load, that all the phases draw equal amount on as load, you could very well end up with where they get amplified, and you'll see a bigger than needed demand on a phase. And that's what you get billed for. So this is considered low-hanging fruit, and we're busy balancing all our dBs just to make sure that the overall effect is a more equally spread maximum demand. Another thing we're also looking at, but we haven't started this yet, like I said, these are next steps, is PID control for some of our processes. Now, here I'm comparing PNID control versus on-off control. And example is, if you've got some heating application, and this is your set point. If you have a heater to control that, and the heater is either on or off, you're gonna be above and below that set point wildly, or the magnitude of your deviations are going to be large. Whereas if you have PNID control, there's no more either on or off of the heater. You can vary the power. That means that you're hovering about your set point much tighter. And we know that is good for process, keeping processes stable, temperature stable. What is not emphasized a lot is that is also good for energy efficiency, because you are only injecting the required energy into the system that you need at the time. And overall, you save energy. Places where you can implement these are, for instance, like it says here, electric and gas heating applications. And there's also dosing systems. But everything's not as rosy as that, because there are some disadvantages. And some of the disadvantages are that they are a bit more complex to implement. And also that if you don't do this properly, you can actually mess up stuff. And then you're going to be famous for the wrong reasons. This is something new. A next step for us is also to look at how we use energy. Now, this is new because this observation that I'm going to talk about now came as a result of a course, a power quality course that the NCPC presented. Now, what you're looking at here is This is a 6 MVA induction furnace. Now, it's usually either on or off. This is not on-off control. These are actual cycles of the machine. But now, this is the normal way to plot the power. You've got power on the y-axis, and you've got the time here. But if you take the same data, and you plot it as a histogram, where power is now on the x-axis, you've got the percentage of time on the y-axis, and this percentage of time is a percentage of this time. This percentage of time is shown by this curve. On the y2 axis, you've got the cumulative result of all those times and powers till it gets to 100%. Now, like I said, this is an induction furnace, and we throw scrap metal in there and we melt it. And after it's melted, we send it on to the next processing line. But now, if you look at this histogram, what you'll see is actually 3 modes of operation. This is at the 6 megawatt MVA power level. So you can see that we were actually melting for only just under 15% of the time. For about 10% and 40% of the time, respectively, we were into different power states. 2 lower energy power states, but they were significant. And this is actually a potential money-saving opportunity. Now, this usually happens because it's a process, one process following onto another. If we melt and the next process is not ready, we have to keep the metal warm, wasting energy. Or if we started the melt too early, we are done with the melt too early, and we also waste energy. But all in all, this is something we need to look at. But like I said, this is something that's new. We discovered it last month, but we'll definitely be looking at it. So that's part of our next steps. Our final next step is to aim for ISO 50001 certification. Because and there are benefits to it. If you just look at it, if you can say you have environmental and quality and energy management certification, you gain a comparative advantage. It boosts the reputation of the company. And what's important, or at least for me, this is what stands out, is that the company proves that it's really, really serious about fighting climate change. People, that is my presentation. Are there any questions? Thank you.
Hi, Andre.
Hi.
I'm Stephen. I just joined Vainan's skills development team, NCPC. You've mentioned your cooling tower water being important, the delta T across there. I'm just wondering, during the period of this project you ran, were you affected by the load shedding, and how's it currently affecting your process?
Okay, when it comes to load shedding, we are in a unique situation. First off, we are based in the Cape Town area, so it's Cape Town municipality. And the Cape Town municipality is usually a load shedding stage lower than what national is. So that's the first thing that causes us to not be affected as much. The other thing is Eskom's got an initiative that they call it's a virtual power station, and they've got an IDR. It's an instantaneous demand response. What they do is that, but first I need to give the context. That power that I showed, that was the power drawn by a 6 MVA furnace. And like you know, that's a melting furnace. From there, it needs to go to a holding furnace, which acts as a buffer. And from there, it goes to where the casting is actually cast. So, seeing that the heat takes about an hour to an hour and 10 minutes, we can easily actually afford to be without power for 10 minutes. We can. So, this Eskom initiative, the instantaneous demand response, what happens there is when Eskom sees that the national grid is under strain, they send us and other customers a signal to drop our load. We then drop our load, and the agreement is that that load is dropped for a maximum of 10 minutes, and it's only for once a day. As a reward for that, doing that, participating in it, we are exempted from stage 1 and 2 load shedding. And when it's stage 3, we have to reduce our load of the previous 24 hours by 15%. When it's on stage 4, we have to reduce the previous 24 hours load with 20%. So we are actually in a favorable position. Okay. That's another question.
Afternoon.
Hi.
My name is Jacob, and I'm coming from the Platinum Incubator in Rustenburg. I just want to ask, since we are talking about industrial efficiency, how, I know additive manufacturing or 3D printing is one of the technologies that are maybe competing or even trying to take out the traditional methods such as casting. So how did you, overcome those kind of challenges or threat, if I may call it, and how did you get to be where you are today? Because I think when this technology was introduced, some of the foundries even had to close. Maybe they didn't have the backbone, but you are still here, and I know your foundry is one of the best in South Africa. So how did you, how did you get to that? Thank you.
Okay, thanks for the compliment. To be honest, 3D printing or additive manufacturing didn't affect us much yet. We don't know what's in the future, but being part of the Daimler Group, there has been advances in using additive manufacturing in manufacturing other components. And together with the additive manufacturing, you also get the regenerative design, where they give you a design that's just as strong, but you use less material. I know BMW has started to use regenerative design as well. I'm not sure if we've started it in the Daimler Group yet. But as far as Atlantis Foundries go, we haven't had challenges due to additive manufacturing yet. And we also don't know how the whole EV is going to affect us.
Just to add to that, 450 kg castings are not going to go through additive manufacturing at this stage. A little bit hard.
Probably not, yeah.
My question is, you have those yellow guys, Eben and Bucky's, and all operating in the foundry now, quite a few of them. I think there are more coming into the foundry, the Fanuc robots I'm talking about.
Yeah.
They all have their little names. Do you think they contributed to saving in energy costs at all? I know they contribute to productivity, and the furnaces probably take up 70-80% of the costs of energy in a foundry. But do you think they've added any value there?
Definitely, yes. The thing about the robots are that if you compare the robots to people, a guy might work different on a Monday compared to on a Wednesday. Now, if you have robots, you have something that's being done consistently. You have a standardized process. And as you know, a foundry operation has a lot of variables, and a change in one variable could maybe lead to changes in other variables. Now, what the robots give you is standardization. With standardization comes a reduction in scrap. Because of that, you get a reduction in rework. Rework takes energy, so it's indirect energy saving. Yes. Okay, another question. Aye.
You showed your energy saving in gigawatt hours, right around 24 point something gigawatt hours. I know as was said just now, the energy used, if it's 31 MVA, it means that 24 gigawatt hours is almost nothing. What was that in percentage saving? And the reason why I'm asking this is there's a lot of initiatives that you guys have done, which is very good. And I just want to kind of, in a way, go to the saying that you have to suffer for beauty. Yeah, you have to do a lot of things to improve, and sometimes the improvement is not that much, but you have to carry on to try and improve little by little. So, just in percentage, what is that of your normal annual kilowatt hours or
In
gigawatt
terms of
hours?
percentage, I don't have an answer for you. I don't think if I should actually give an answer if I knew, because that can allow you to calculate our capacities. But no, that's just our electrical supply. But what I can tell you is that we saved, but that's for 7 years. We saved 27 mil worth of energy, of money that we would have spent on electricity. Say again? Yes. Yes, the rebate that we got was 7.4 because it's 27 or 28% of the money that you would have spent that you get as a rebate.
Under 10%?
Nah, you're pushing for an answer. I don't know. I only looked at our metric. That's the one that's important to me.
Andrew, thank you very much. Just a round of applause for Andrew.